Hello, welcome to EEE 101 again. Today we will discuss Thevenin's theorem. Thevenin's theorem is actually one of the most important circuit theorems which is widely used in different branches of electrical engineering such as electronic circuits, power systems, and communication engineering. Let us consider a two-terminal circuit. A two-terminal circuit may have many nodes and many circuit elements, but we are interested in the behavior of the circuit between two nodes A and B. A load is connected between node A and node B. The voltage across the load is VL and the current flowing to the load is IL. Thevenin's theorem says that this linear two-terminal circuit can be replaced by an independent voltage source VTH in series with a resistance RTH. If this two-terminal circuit and the voltage source in series with the resistance are equivalent, then for both cases the load voltage VL will be the same and the load current IL will be the same. If we want to state Thevenin's theorem formally, it can be said that a linear two-terminal network may be replaced by an equivalent circuit which consists of an independent voltage source V Thevenin in series with a resistor R Thevenin. Now the question is, if the linear two-terminal circuit is known, how do we find the value of VTH and the value of RTH? So this is the question that we will answer next. Finding VTH is actually straightforward. To find VTH, we remove the load from the two-terminal circuit connected between node A and node B. The voltage VOC, which appears between node A and node B under open circuit condition, is equal to VTH. So to find VTH, we simply disconnect the load between node A and node B, and under this open circuit condition we find out VOC, and that gives us VTH. To find RTH, there are three different techniques available. Let's discuss the techniques one by one. First, case 1. Case 1 applies to those circuits which do not contain any dependent source. That means the linear two-terminal circuit consists of only independent sources and resistors. In that circuit, we will start by deactivating all independent sources. So we get the linear two-terminal circuit with all independent sources deactivated. Because the circuit does not have any dependent source, we are left with only resistors within this network. So this circuit essentially is a network of resistors. If we have a network of resistors, we can find the equivalent resistance between any two nodes. In this case, we will find the equivalent resistance RAB between node A and node B. This RAB is equal to RTH. So if we want to summarize case 1, first step, we deactivate all independent sources. In the second step, we calculate the equivalent resistance between node A and node B, and the equivalent resistance gives us RTH. When can we apply case 1? Case 1 is applicable when the linear two-terminal circuit does not contain any dependent source. Okay, next we will discuss special case. The special case is not discussed formally in your textbook written by Alexander. However, for many practical purpose, this is very important. So I am considering it as a separate case. Okay. In special case, we do not deactivate any independent sources. We measure or calculate two data sets. First, We disconnect the load between node A and node B, and under open circuit condition, we find the voltage VOC. Actually, we have to do this step anyway when applying Thevenin's theorem to a circuit because VOC is equal to VTH. If we look at the equivalent circuit, the Thevenin's equivalent circuit under open circuit condition looks like this. The voltage VOC between A and B is VTH because there is no current in this circuit, so the voltage drop across RTH is 0. Next, we will make a short circuit between node A and node B. Again, all independent sources remain active in our two-terminal circuit. Now, we calculate or determine the short circuit current ISC. In the equivalent Thevenin's circuit, this looks like this. So, using Ohm's law, we can write that ISC is VTH by RTH. So, rearranging the terms, RTH is VTH by ISC, but VTH is VOC. So, RTH is VOC by ISC. According to the special case, Thevenin's equivalent resistance RTH is the ratio of the open circuit voltage between node A and B and the short circuit current between node A and B. When calculating open circuit voltage and short circuit current, we need to remember the correct polarity of VOC and ISC. If we look at the upper diagram and lower diagram, node A is the node where plus of the VTH is assigned and minus of the VTH is assigned at node B. In the bottom circuit, ISC is flowing from node A to B, that is flowing from the node where plus of the voltage VTH is assigned towards the node where minus of the voltage VTH is assigned. Next, we want to know when can we apply special case to determine RTH. Special case is applicable when the two-terminal circuit contains one or more independent source. That is, the two-terminal circuit must have at least one independent source. If there is no independent source in the two-terminal circuit, special case cannot be applied. If you compare case 1 with special case, you will find an interesting difference. In case 1, you had to go inside the two-terminal circuit and deactivate all independent sources. But in special case, you don't need to go inside the two-terminal circuit. So in practical situations where you do not have any access inside the two-terminal circuit, special case may be more suitable to find RTH than the case 1. Okay, finally, we will talk about the third technique which we call case 2. The first step of case 2 is similar to that of case 1, but before we go into the details, let's try to understand the origin of case 2. The two-terminal circuit is replaced by Thevenin's equivalent here with VTH and RTH. We remove the load and between node A and B, we apply a test voltage source whose value VTS is known. We know the value of VTest. And if we can determine the value of ITest, can we say that RTH is VTest by ITest? Actually, we cannot because there is another voltage source VTH. So if we want to apply Ohm's law and find out RTH in this circuit, we have to make sure that the value of VTH is 0. If VTH is 0, this will act like a short circuit, and using Ohm's law, I can say RTH is equal to VTest by ITest. So RTH is indeed VTest by ITest only if VTH is equal to 0. But the question is, How do I make VTH equal to 0? Remember that VTH is equal to VOC, the open circuit voltage. The open circuit voltage between node A and B is due to the contributions of all independent sources within the two-terminal circuit. If we deactivate all the independent sources within the two-terminal circuit, there will be no cause, so VOC will be equal to 0. So, an appropriate way to make VTH 0 in the two-terminal circuit is to deactivate all independent sources. So this is what is stated here. VTH can be made 0 by deactivating all independent sources in the two-terminal circuit. So this step is similar to the first step of case 1. Okay. So we have two possible ways to apply case 2. In the first case, we have the linear two-terminal circuit with all independent sources deactivated. Between node A and node B, we apply a test voltage source whose voltage Vtest is known. In theory, Vtest can have any value as long as we know the value. But for simplicity, we often choose Vtest equal to 1 volt. So for this 1 volt test voltage source, we will determine the value of Itest. And once we know Itest, RTH is straightforward, equal to Vtest by Itest, but Vtest is 1 volt, so RTH is 1 volt by Itest. Instead of applying a test voltage source, we can do the same procedure by using a test current source. So let's look at this circuit. Between node A and B, instead of a test voltage source, we have applied a test current source whose value Itest is known. Again, Itest can have any value. The result does not depend on the value of Itest. But for simplicity, we choose Itest to be 1 ampere. So for this 1 ampere test current source, we will find the value of the voltage Vtest. And once Vtest is determined, as in the previous procedure, RTH is Vtest divided by Itest, which is Vtest over 1 ampere. Now, we should be careful about one thing, that is the relative polarity or relative reference of Itest and Vtest. If we look at all the diagrams, you will see that Vtest and Itest do not satisfy passive sign convention. That is the important thing you need to remember. When applying case 2 to find RTH, there are two important things that you should consider. First, do not forget to deactivate all independent sources. Second, make sure that your chosen reference for Vtest and Itest are such that they do not satisfy passive sign convention. Finally, we want to know in which circuits can we apply case 2. Actually, case 2 is applicable for all combinations of independent and dependent sources. We can apply case 2 if the circuit contains only independent source. We can apply case 2 when the circuit contains both independent and dependent sources. And we can also apply case 2 when only dependent sources are in the two-terminal circuit. So we can say that case 2 applies always. Case 1 applies when there is no dependent source. Special case applies when the circuit contains one or more independent sources. But source-wise, case 2 is always applicable. Okay? So you may ask, why learn all three techniques? If I only learn case 2, I can find out RTH for any circuit. That is correct. But conceptually and procedure-wise, case 2 is the most complicated approach. For simple circuits, often case 1 and case 2 allow you to find out RTH more easily. So it is better to learn all three techniques. Now that we know how to find VTH and RTH, in other words, how to find Thevenin's equivalent circuit, we can apply Thevenin's theorem to solve electrical circuit problems. Let's look at one example. In this circuit, we want to calculate I naught through the 1 ohms resistance using Thevenin's theorem. To apply Thevenin's theorem, we have to partition the circuit into two parts first. One part is the load, the other part is the two-terminal circuit. So we draw this line to separate the load from the left of the circuit. The 1 ohms resistance is load and the rest of the circuit is the two-terminal circuit. And the two nodes between which the load is connected, we call them A and B. So Thevenin's equivalent circuit is to be determined between node A and node B. First, we want to find out Thevenin's voltage, VTH. To determine VTH, we remove the load resistance and make an open circuit between node A and B. So this is the circuit we have. This is node A and this is node B. The voltage VTH is between these two nodes. I have grounded node B because I want to calculate VTH using nodal analysis. We have a node where three circuit elements are connected, 6 ohms, 6 ohms and 2 ampere, and let's say the voltage of this node is V1. Normally, we do not assign a node voltage to a node where only two circuit elements are connected, but we have made an exception here. Why did we assign VTH voltage to this node A where only two circuit elements are connected? Because VTH is the voltage, that is the voltage of node A is the voltage which we want to determine. So we have two unknown voltages, we need two node equations. These are straightforward and as shown here, for V1 there are two resistances on the left hand side and one current source on the right hand side. For VTH we have only two resistances on the left hand side. If we solve these two equations, we find out that VTH is equal to 6 volts. Okay. Next, we have to find RTH. If we look at this circuit, the two-terminal circuit, there is no dependent source. We have only independent sources. Case 1 is applicable. We have two independent sources. So special case is also applicable and case 2 is always applicable. We can determine RTH using any of the three techniques that we have discussed. Usually, you don't need to apply multiple techniques to determine RTH, but to test our knowledge of RTH calculation, we will calculate RTH of this circuit using all three techniques and then we will verify if we get the same result. Okay. First, we consider case 1. In case 1, we deactivate the independent sources and find Req. If we deactivate the independent sources, this is the circuit we get. The independent current source is replaced by an open circuit. The independent voltage source is replaced by a short circuit. And our interest is between node A and node B. So RTH is equal to the equivalent resistance between node A and node B. Between A and B, we observe that 6 ohms and 6 ohms are in series. The series combination is in parallel with 4 ohms. So RTH is 6 plus 6 in parallel with 4, which is equal to 3 ohms. So case 1 gives us the value of RTH, which is 3 ohms. Now let's look at special case. In special case, RTH is VOC by ISC And we recall that we do not deactivate any independent source in special case. So the VOC we have already found out when we calculated the VTH. VOC is 6 volts. In addition, we need to determine ISC. Okay, we have this original two-terminal circuit and we make a short circuit between node A and node B. And we are interested in the current ISC flowing through the short circuit. This 4 ohms is in parallel with this short circuit. So 4 ohms is inactive. We can remove this 4 ohms without changing the behavior of the circuit. There are many different ways to calculate ISC. You can use mesh analysis, you can use source transformation, and so on. I will apply nodal analysis. So I have grounded node B and I apply a voltage V2 to this node where 6 ohms, 6 ohms and 2 ampere are connected. 4 ohms is gone, so two resistances are connected at V2 voltage and a current source is also present. Writing the node equation, we solve that V2 is equal to 12 volt. Because 4 ohms is not there, ISC is the current flowing through 6 ohms. The voltage at the left end of 6 ohms is V2. The voltage at the right end of 6 ohms is 0. So ISC is V2 over 6 ohms, which is 2 ampere. VOC is 6 volts, ISC is 2 ampere. That means RTH is 3 ampere, which is the same value that we obtained from case 1. Finally, we apply case 2. In case 2, we deactivate all the independent sources and apply either a test voltage source or a test current source between nodes A and B. In this case, we have deactivated the independent current source by an open circuit. We have deactivated the independent voltage source by a short circuit, and we have applied a test current source, a 1 ampere test current source between node A and node B. Vtest is the voltage between node A and node B. Vtest and Itest should not satisfy passive sign convention. So the plus of Vtest is at node A and the minus of Vtest is at node B. I have grounded node B because I want to apply the nodal equation. Vtest is the voltage of node A. So if I look at node A, 6 ohms and 6 ohms are in series. There are two resistive branches and a current source branch. So this is the node equation. If we solve it, we find out Vtest is 3 volts. Now RTH is Vtest over Itest. Itest is 1 ampere. So RTH is 3 ohms. Again, this is the same result that we have obtained from case 1 and special case. So you can see that you can choose any appropriate technique to find RTH according to your preference. But remember, if you choose a technique which is not applicable, then the result will be incorrect. Now we want to return to our original problem. We wanted to calculate the current through the 1 ohms load resistance. So here we replace our two-terminal circuit by the Thevenin's equivalent. VTH is 6 volts, which is in series with RTH, that is 3 ohms. Between node A and node B, we have reconnected our 1 ohms load and I0 is the current flowing through the load. These 3 ohms and 1 ohms are in series, so we can find out I0 by Ohm's law. I0 is 6 volts divided by 3 ohms and 1 ohms in series, so the resulting value of I0 is 1.5 ampere. So this example illustrates us how to apply Thevenin's theorem to solution of electrical circuits. That's all for today. Thank you.